Hi guys, today we are going to learn about cyclic groups. We will define cyclic subgroups, cyclic groups, then we will see some examples and some properties. Here are the books we are going to follow. Contemporary Abstract Algebra by Galen and First Course in Abstract Algebra by John B. Farley. Well, we already have proved that the set of all integral powers of an element of a group becomes a subgroup. So this simply leads to the following definition, that we have a group and then we take an element from the group G, then the set of all powers of this A becomes a subgroup. Such a subgroup is called a cyclic subgroup generated by A. And in case the group is additive, then we denote it by the powers. They are actually denoted by NA. Here are some examples. We take 2 from the Z6. It's a group under addition modulo 6. Then all powers of A are actually 0 to 4. So this is a cyclic subgroup generated by 2. Similarly, if we take 3 from U10, we will get 1, 3, 7, 9, and we call it a cyclic subgroup generated by 3. Similarly, in example 3 and 4. In example 5, we see if we consider Z11 and take 1 from Z11, then actually it generates this single element 1 generates the entire group Z11. So that's quite interesting situation, that a single element is generating the entire group. So this leads to the definition of cyclic group. So by definition, a cyclic group is actually a group if there is an element, say A, such that that element generates the entire group G. So in that case, we call this A is a generator of J. So cyclic group simply means a group if it is generated by a single element. Here are some examples. Set of integers is generated by 1. So it's a cyclic group. So we note that minus 1 is also a generator of this Z. So it means generator may not be unique. There could be many generators, as we see in case of Zn, for example. So this Zn is cyclic, generated by 1 with the operation addition modulo n. Similarly, this minus 1 is also generator. So Zn may have many generators, but actually it depends on the n. So for example, in Z8, 1, 3, 5, 7, all these are generators of Z8. In case of U10, 3 and 7, these two are generators. So Z8, U10, Zn, all these are cyclic groups. If we consider U8, we see none of the elements of U8 generate this U8, so that's why we say this U8 is not a cyclic group. Here we have to discuss some properties of cyclic groups. The first one is every cyclic group is abelian. So we consider a cyclic group, say generated by A, then that's the definition, that it is generated by this A. So we have to prove that it is abelian. It means we need to consider 2 elements from the group J, and then we have to prove that these two commute. That is, if we compute xy and yx, they are the same. So by definition, if we take xy from J, then it means there exists some L and M such that these xy can be written in the power of A. So now we compute xy. So by this, xy is replaced by A raised to L, A raised to M, and now simple calculations show that it is actually yx. So it means the group is abelian. That's fine. Next we have an interesting property that a subgroup of cyclic group is cyclic. That is, if we consider a cyclic group, then all subgroups of that cyclic group are cyclic. There are two parts in the proof. We consider a cyclic group generated by say A, and we have a subgroup. We need to show that this H is cyclic. So there are two possibilities. For example, if this H is equal to the neutral element, that is trivial, that is H is nothing but it contains only the identity element, then it's quite simple. Then it becomes cyclic, because if we take all powers of the neutral element, it gives neutral element, so then it becomes a cyclic group. The next, in case this H is different from this E, then we need to prove that it is cyclic. Okay, because this H is a subgroup of G, then it means in G there are powers of A, so it means if A n belongs to H for definitely for some element n, some integer n, because there is an order in the integers, so we can assume that say m is the smallest in Z such that am belongs to H, then we need to actually prove that this am generates this H, that is every element in H can be written as a power of am, or in other words C by this notation. Yeah, we must show that every B is a power of C. Okay, since B belongs to H and H is actually a subgroup of G, it means B can be written as in the power of A for some n. So by Devian algorithm we can write there exist integers Q and R such that n is equal to mq plus r, and definitely this r is less than m. Replace this n by mq plus r, and simple calculation show that AR can be written in this form. Because H is a subgroup, it means this AR belongs to H. Okay, but as by assumption this m was the smallest positive integer that belongs to H, and now we see AR also belongs to H, because this r was less than m, so we have the only option left is r must be 0. So when r is 0, then it means n is actually qm, and if we replace this n by qm, we will see b is actually the power of c, and we are done. Here is another interesting property. So there are actually three parts in this theorem. So we have a group, we take an element from that group G. Okay, if A has finite order, then A raised to I equal to A raised to J. It's a typing mistake here. A must be raised to J, so this J should be here in the power. So if and only if I is equal to J, and if A has finite order, say n, then the group generated by A is actually E, the neutral element, then A, then square up to A n minus 1, and AI equals AJ if and only if n divides I minus j, that is the difference of these two indices. So there are three parts in this proof, the part 1. So first we assume that the order is infinite. Okay, it means there does not exist any positive integers which gives an equal to A. So if AI is equal to AJ, this can be written as A raised to I minus j is A, and the only option left is I minus j is 0, or simply they are equal. In the second part, we have to prove that the generated by A, the group generated by A is actually nothing but consisting of the elements E, then A square, and so on up to n minus 1, with the assumption that when it has finite order. So it's quite clear that these powers are distinct, because if we assume that okay, these are not different, say they are the same, then we will get a contradiction, because definitely this j, say less than I and I is less than n minus 1, then we will get E, definitely it will contradict because the order of A is n. So all these powers, they are distinct. Okay, so we take some power from here, because here in this set there are actually powers of A. We consider some power of A, say k. Then by Devian algorithm we can write in this form: k is equal to qn plus r. Definitely r is less than n, so we replace this k by qn plus r, and simply it can be written as ar. So look here, now this ak can be written as power of again A, so it means it belongs to this set, and this simply means this generated by the group generated by this A is nothing but EA square, and so on up to n minus 1. In the third part, we have to show that, of course, the order is finite here. This AI is equals J. Then we need to show that n divides I minus J. Again we will use Devian algorithm here. So by assumption we can write A, I minus J is A. Again by Devian algorithm we can write in this form. Of course this R is less than n here, and simple calculations show that this is nothing but A raised to R is actually E, because n was the least positive integer by definition. So an gives A, n is the least here, but we see here AR also gives A, so it means the only option here we have R is 0. So when R is 0, then by definition of division of integers, n divides I minus J. Okay, so that's it. On the other hand, if we assume that this n divides I minus J, then by division of integers, this can be written as I minus J is nq, and if we replace this I minus J by nq, we can write it AI is equal to aj. We have a short corollary that's quite simple. If we take any element, then the order of A and the order of this cyclic group generated by A, that's the same. So it immediately follows from this part, the second part of this theorem. Quite simple. And there's another corollary that directly follows from the above theorem, because if AK is E, and we can simply write AK is E and A raised to 0 is also A, then it means n divides K. There's another interesting property. We have a group, we take an element from the group J. If we assume that order of A is n, then what happens? Then the cyclic group generated by A raised to K and the cyclic group generated by A raised to the greatest common divisor of nk, they are same, and the order of AK is actually n divided by the greatest common divisor of nk. Just to simplify the notation, we denote by D, the greatest common divisor of n and k, with because it's the greatest common divisor, so we can write, for example, in this form. And AK simply can be written as A raised to D then R, because it's written in the power of this, so we can say the cyclic group generated by AK is contained into the cyclic group generated by this D. So I suggest you should recall the greatest common divisor, its properties from the course on number theory. So this D can be written as NS plus KT. So I repeat, you should recall the properties of greatest common divisor from the course number theory. So AD is now replaced by NS plus KT. A simple calculation show that this is nothing but A raised to KT, which simply means, because it's a power of AK, so it means it belongs to a cyclic group generated by AK, and simply it means A raised to D is contained into this, and this was the reverse inclusion, so it means we have proved that these two are actually the same. Because this D was the greatest common divisor, it divides definitely N, so we see A raised to D, and then this N divided by D is nothing but AN, and because N was the order of A, so it means it gives this A. So this simply means that order of AD cannot exceed N divided by D. Okay. For example, if we take any natural number less than N divided by D, then we see it cannot be, because of the definition of the order. So it means the order of A raised to D is nothing but N divided by D. There is an immediate consequence of this theorem that if the order is N, then cyclic group generated by AI and the cyclic group generated by AJ, they are same if and only if the greatest common divisor of NI and NJ, they are same. Similarly, if these greatest common divisors of N with I and J, they are same, then the order of AI and order of AJ, they are also same. That's quite simple. And there's another one, nice one. If the order is N and the cyclic group generated by A is equal to cyclic group generated by AJ, if and only when the greatest common divisor of N and J is 1, it means when N and J, they are relatively prime. Similarly, the order of A and order of cyclic group generated by AJ, they are same when the greatest common divisor of N and J is 1, or otherwise they are co-prime. We can use this to solve many exercises related to generators. For example, if we are given a generator of a cyclic group, then we can use this interesting result to compute the remaining all other generators of that group. So here's a simple example. We consider U25, so we see the order is 20 and it is generated by 2. So what we have to do, we have to compute all the powers of 2, but only those powers which are co-prime with 20. So we compute 2 raised to 1, 3, 7, 9, 11 and up to 23. And then we see simple calculations show that we will get 2, 8, 3, 12 and so on. So it means all these are generators. So these were some interesting properties of cyclic groups. There are also many other properties related to structure, so we will learn in the coming lectures. Here are some exercises. In the first, you need to compute the generators of Z6, Z8 and Z20. The second exercise is very interesting because we have proved that if we have a cyclic group, then all the subgroups, they are cyclic, but the converse is not true. So here you have to find an example that if all the subgroups are cyclic but the group may not be cyclic. Okay, and the third, you have to prove that the cyclic group generated by A and its inverse, they are actually same. Thank you very much.